Okay, now this one I want to call bipolar junction transistor biasing. And biasing refers to how we're going to set up the DC portion of our transistor circuit. And again, what our goal is to be able to take a very small AC signal. I'm showing one here, it's like a millivolt, and put that into the base of my transistor and get a much larger copy of it at the collector, which is my output. Now, the problem we run into is that it takes 7/10 of a volt, or 700 millivolts, to turn that base emitter junction on. And if that base emitter junction is not turned on or forward biased, nothing's going to happen. And 1 millivolt of AC doesn't even come close. And matter of fact, the negative half of that's going in the wrong direction. So what do? We add some DC bias to turn that transistor on, and it's going to be the 7/10 of a volt there, 700 millivolts plus some more. And it turns out we're going to need to add a resistor here, really, between there and ground to get it biased up where we want to. Now, you can use a base supply the way we have here, but that limits us in some ways. It's much better if we do it a different way. If we take our collector supply, which we've got connected to the collector already. I don't have room to show all the resistor here and everything, but we use a volt. We'll run it through a resistor into the collector, but then we'll also use a voltage divider to divide it down and put it into the base, a smaller version of it. That way we can turn that base emitter junction on and bias our transistor so that the transistor is already turned on by the DC, so that when the AC comes in, it does get amplified the way that we want it to. All right. Now, I pre-drew this slide because there's a lot of drawing there, and I'm a poor enough artist and have enough trouble with the stylus on this computer screen that it took lots of erasing and doing over to get it this good, as bad as that looks. We'll see what we've got here. I've got my collector and emitter both connected through resistors, emitter to ground, collector to the collector supply voltage. We'll worry about the base later. Right now I'm just worried about the collector and emitter side of the transistor. Now, these are my collector curves that we looked at last time. Now here I'm doing the base current in microamps. It makes the numbers work out a little better, and that's more typical really. So I've got 0, 5, 10, 15, 20, 25 microamps over here. And each one of these curves corresponds to a different value for base current. And I'm plotting collector current on the vertical axis versus VCE, collector emitter voltage, on the horizontal axis. Now I've chosen actual values this time for the resistors, because it makes a difference. I've chosen an actual value for my collector supply voltage. And now I want to construct something that we call a load line. It's supposed to be an I. There we go. Load line. And what that's going to do, that's going to draw a diagonal line across these curves that is set by these values we've chosen for collector supply, collector resistor, and emitter resistor. The curves as they are right now show me all the possible values that current and voltage can take in any circuit. What the load line is going to do is narrow it down. Since I've chosen particular values for VCE, RC, and RE, that line narrows it down to those choices, all the values IC and VCE can have together given these choices. And the way that we find the load line is we find the two endpoints and draw a line that connects them together. On the vertical axis, well, let's say the horizontal axis first. We want VCE equals 0. Now, my curves don't go all the way to 0. There's a little gap between the horizontal axis and the saturation point of the transistor. Let me get my pointer right here. See the gap? But that gap is typically only about 1/10 of a volt or so. So for this exercise, we typically just ignore that gap. And we set VCE equal to 0. Just on, now we're not going to do that in the actual circuit, but we're on paper or on a whiteboard. We're going to say what happens if VCE is 0. Well, that says the whole VCC supply voltage has to drop across the two resistors. And I can find the current then, just as a resistor circuit. It's 15 volts over 6K plus 1.5K. 6 and 1.5 give me 7.5 into 15. That'll give me 2 milliamps. So when VCE is 0, IC is 2 milliamps. That's going to give me this point right here. Again, ignoring the little gap there. Now, the other point we need to find is what happens when IC is 0. That puts us on this horizontal axis. That'll give us our other end point of our load line. And that one's even easier to do than the one we just did. If we set IC equals 0, there's no current flow through the resistor, so their voltage drop is 0. So Kirchhoff's voltage law says the entire supply voltage has to drop across VCE. Let me put it down below here. So when IC is 0, VCE is 15 volts. Right there is my point for that. So now, let's draw a diagonal line that connects those two, and that is my load line. So now, if I have that part of the circuit done, no matter what I do with the base, since I've chosen this value for collector and emitter resistors and collector supply voltage, my IC VCE combination is going to be somewhere on that line. And we want it to be right here in the middle somewhere. And we can do that by choosing the base circuit that we need to get us there. We need a collector current of about 1 milliamps, what we're shooting for. So that means we need a base current of approximately 10 microamps. Remember, my base current's in microamps for this example. Now, if we do that, we'll look at that in a minute. If we do that, that's going to give us an operating point. Once, this is the curves I got. The load line that I have right now assumes we've chosen VCC, RC, and RE. We have not yet chosen IB or VB or anything at the base. So that gives us anywhere on the line. Once we do choose the base circuit, it's going to give us a single point on that line. And we want it to be right there. or thereabouts. And we call that the operating point, or the Q point. The Q stands for quiescent. Now, when I add AC to that, quiescent means quiet, basically. Fancy word for quiet. So with no AC added, the transistors are going to stay right there, nothing moves. When I add AC to it, the voltage and the current's going to move around, up and down around that point. If I get that point too close to the top here, some of my AC gets lost. I'll end up with an output that looks like this. See how it's chopped off there? And if I get too close to this point, it gets chopped off at the bottom. So that's why we want that Q point right in the middle, as close as we can get it. That gives us the most dynamic range, we call it. The bigger I can let that AC output become without chopping something of it off. Okay, let's go. Let's see, it's just 11 minutes so far. Let's go to another slide now. This is the bias circuit we're going to use for transistors in general. I've got a resistor here we're going to call R1. Another resistor here we're going to call R2. And those two resistors form a voltage divider. Now, I don't know how much time you spent on voltage dividers in the DC class last semester, because I didn't teach that one. But if I have a circuit here, I'm going to add the transistor later. Let this be my VCC. And this is going to be my base. But for right now, we're just going to call it the output of the voltage divider. Now, that's just a series circuit. All right. It's kind of drawn backwards from the way we usually do it. What if I wanted to know the current in that series circuit? Well, I'd find total resistance. And then the current would be and I'm going to go ahead and write it out this way. Same thing as if you just put RT on the bottom. And if I want to know the voltage drop across either one of the resistors, let's say R2 is really the only one I'm really interested in here. And that's my output voltage. You see, if I measure from here to ground, my output there to ground, that's V out. Well, it's R2 times I, but we can shorten that, and I ran out of room down there. Well, no, I can do this. So for any given VCC, I can choose to make that output voltage whatever I want to. I can choose my resistors so that I can make anything I want to. Now, I'm going to connect that output to the base of my transistor in a minute. So this is going to be IB. and we'll call this one. Now, the two currents through R1 and R2 are not the same because some of that current has split off and gone to the base. But what we're saying here is that that base current is so small compared to IS, and that's much, much greater, that as far as those two series resistors are concerned, we can ignore the base current and just treat that as a series resistor circuit. It's not a pure series resistor circuit, as I say again, because I'm going to connect the transistor here. And I'm getting up to around 15 minutes again, so I think I won't stop and continue this on in the next video. But I want to make the point, I'm going to have a resistor, or rather a transistor, an emitter resistor, a collector resistor. I'll go ahead and draw them in real quick. So it's going to look like that if you can see it through all the mess there. So it's not a pure series circuit. There's a parallel combination. Find my pointer again. There it is. There's a parallel combination here if you wanted to do the circuit for real. And there's also a parallel combination there. But again, because the base current is so small and you have to choose resistors, you would only use mega ohms there. It's usually something in the kilo ohm range. But if that base current's microamps, if you made it a few milliamps, then you're a lot bigger here. And again, the base current is negligible as far as these series resistors are concerned. So I'm going to stop there. It's nearly 17 minutes and continue this on in one more video.